morning, students. Yesterday we started the topic colligative properties, and we have studied about two colligative properties. First is the relative lowering in a vapor pressure, and second is elevation in boiling point. These two colligative properties we have studied yesterday. Now we are going to start the third colligative property, that is the depression in freezing point. Depression means decrease in freezing point. First of all, we have to understand what is the freezing point. We know it is the temperature at which solid and liquid state of a substance, and it is the temperature at which solid and liquid state of a substance are in the state of equilibrium. Mean at freezing point, solid state and the liquid state of the same substance will be in the state of equilibrium. Mean at this temperature, the rate of melting of solid will be equal to the rate of freezing of liquid. For example, at 0 degree Celsius temperature and 1 atmosphere pressure condition, ice and liquid water will be in the state of equilibrium, which means that at 0 degree Celsius temperature and a pressure of 1 atmosphere, rate of melting of ice will be equal to rate of freezing of water. One more thing, solid and a liquid state of the same substance will be in the state of equilibrium only when the vapor pressure of solid and liquid state of the substance will be equal. It means freezing point can also be defined as, and we can write the temperature at which vapor pressure of solid and liquid state of a substance becomes equal to each other. The temperature at which vapor pressure of solid and liquid state of substance became equal to each other is also called freezing point, or we can say melting point. For example, at 0 degree Celsius, vapor pressure of solid ice will be equal to vapor pressure of liquid water, and this 0 degree Celsius can be called freezing point of water. Any the temperature at which vapor pressure of solid and liquid state of a substance become equal, that will be the freezing point of that substance. Again I will repeat, at 0 degree Celsius temperature, vapor pressure of ice is equal to vapor pressure of liquid water, and at this temperature, ice and water will be in the state of equilibrium. I written H2O solid, that is ice, and H2O liquid, that is liquid water. And at 0 degree Celsius, the rate of melting of ice will be equal to rate of freezing of water. So this is the temperature at which ice and water will be in state of equilibrium, and it can be called freezing point of water. Now we come to our qualitative property, that is the depression in freezing point. First of all, you take one example. Suppose we have pure water and this aqueous sugar solution. We know the vapor pressure of pure water. If I write P naught A and vapor pressure of this sugar solution as Ts, so we know P naught A is more than Ps at any temperature. And vapor pressure of pure water will be more than vapor pressure of aqueous sugar solution. Or in generalized thing, we can say the vapor pressure of a solution containing a non-volatile solute is always less than the vapor pressure of pure solvent. Now you see, as the vapor pressure of pure solvent is high, then the vapor pressure of solid and liquid state of pure solvent will be equal to each other at some higher temperature. What I am saying, I will repeat it. The vapor pressure of solid and liquid state of a pure solvent will be equal to each other at some higher temperature, because the vapor pressure of pure solvent is higher than solution. But the vapor pressure of solution is less. Yani vapor pressure of solution containing non-volatile solute is less. So the vapor pressure of solution, yani liquid state of solution, became equal to vapor pressure of solid state of the solvent at some lower temperature. It means the freezing point of a solution containing non-volatile solute will be lower than the freezing point of pure solvent. What I told, I will repeat. I am telling the freezing point of a solution containing a non-volatile solute will be lower than the freezing point of pure solvent. Mean a solution containing non-volatile solute freezes at a lower temperature than the temperature at which pure solvent freezes. That we will understand from this graph. If I take vapor pressure on y-axis and temperature on x-axis, vapor pressure of solvent and vapor pressure of pure solvent can be given by this curve. And this is A, this B, this C point. AB curve represents the vapor pressure of solid state of the solvent, and B to C curve represents the vapor pressure of liquid state of the solvent. Once you see this curve A, B, C represent the vapor pressure of pure solvent versus temperature, and now you see AB curve represents the vapor pressure of solid state of the solvent, and B to C curve represent the vapor pressure of liquid state of the solvent. So you see at point B, the vapor pressure of solid and liquid state of substance in solid and liquid state of the solvent is equal. So the temperature corresponding to B point can be called freezing point of pure solvent. It means this is the freezing point of pure solvent at which vapor pressure of solid and liquid state of the solvent became equal. But we know the vapor pressure of solution containing non-volatile solute always has, yani vapor pressure of solution containing non-volatile solute is always less than pure solvent. So vapor pressure of solution became equal to vapor pressure of solid state of the solvent at some lower temperature. And which temperature at which vapor pressure of solid solvent became equal to vapor pressure of solution containing non-volatile solute will be freezing point of solution. Here I can write this curve D to E. This curve D to E represent the vapor pressure of solution containing a non-volatile solute. And at point D, the vapor pressure of solution and the vapor pressure of solid state of solvent became equal, and the temperature corresponding to D point can be called freezing point of the solution, that I written as TF, and the freezing point of pure solvent is written as TF naught. And from here it is clear the freezing point of solution containing non-volatile solute is less than the freezing point of pure solvent, and this difference can be written as delta TF. So here this delta TF is the TF naught minus TF. This delta TF is the decrease in freezing point, or you can say depression in freezing point. And depression in freezing point of solution containing non-volatile solute will be equal to freezing point of pure solvent minus freezing point of solution containing non-volatile solute. Here again, if we come to this example, we know the freezing point of pure water is 0 degree Celsius under condition of 1 atmospheric pressure. But freezing point of aqueous sugar solution, which contain a non-volatile solute, that is sugar, has freezing point lower than that of pure water. Means this sugar solution will freeze at a temperature below than 0 degree Celsius. If pure water freezes at 0 degree Celsius, aqueous sugar solution will freeze below than 0 degree Celsius. And difference in freezing point of pure water and freezing point of this aqueous sugar solution can be called depression in freezing point of the solution. Now you see this delta TF, that is the depression in freezing point of solution, is found to be directly proportional to molarity of solution containing non-volatile solute. Yani practically delta TF is found to be directly proportional to molarity of solution containing non-volatile solute. And we know molarity is number of mole of solute present per kilogram of solvent. Here delta TF can be written equal to Kf into L. Here Kf is the proportionality constant and this proportionality constant is called cryoscopic constant, or it is called molar depression constant. Here Kf is a cryoscopic constant or molar depression constant, and Kf depend upon the nature of solvent, and value of Kf will be for different for different solvent. For example, Kf for water, yani molar depression constant of water is 1.86 Kelvin kilogram per mole, and Kf of camphor is almost 39.7 Kelvin kilogram per mole. Here already I told molar depression constant depend upon nature of solvent and value of Kf will be different for different solvents. Now how we can define Kf? Yani what is molar depression constant? Yeah, what is cryoscopic constant? So I can say it is the depression in freezing point of a solution containing 1 mole of solute, यानी 1 mole of non-volatile solute in 1 kg of solvent, 1 kilogram of solvent. Or we can say this definition came from here. You see, delta Tf is equal to Kf into m, and if I take m equal to 1 mole per kg, तो delta Tf will be equal to Kf only. So molar depression constant is the depression in freezing point of a solution whose molarity is 1. Kf is the depression in freezing point of a solution whose molarity is 1, whose molarity is unity. You see, the molar depression constant of water is 1.86. What does it mean? Yani Kf of water is 1.86 Kelvin kilogram per mole, which means that, and it means that when 1 mole of a non-volatile solute is dissolved in 1 kilogram of water, the depression in freezing point of solution, depression in freezing point of solution will be 1.86 Kelvin, or you can write 1.86 degrees Celsius. We will understand it with one more example. You see, suppose it is pure water and its freezing point is 0 degrees Celsius, or you can say 273 Kelvin. Now if we take a solution containing 1 mole of sugar, that is a non-volatile solute, in 1 kg of water, the freezing point of this solution will be 1.86 Kelvin less than that of freezing point of pure water. Mean the freezing point of this aqueous solution containing 1 mole of sugar in 1 kg of water will be, that is 271.14 Kelvin. And this aqueous solution which contains 1 mole of sugar in 1 kilogram of water will freeze at 271.14 Kelvin, and its freezing point will be 1.86 Kelvin below than, lower than freezing point of pure water. It means when we add 1 mole of any non-volatile solute in 1 kilogram of water, the depression in freezing point of solution will be 1.86 Kelvin, or in degree Celsius we can write 1.86 degrees Celsius. Now you see what will be the unit of Kf. So we know delta Tf equal to Kf into m. So Kf can be written delta Tf by m. We know delta Tf is the depression in freezing point and it can be taken in Kelvin, and m is the molarity of solution and it will be in mole per kilogram. So we can write the unit Kelvin kilogram per mole. This unit is same as unit of kb. So kf and kb both have the same units, and unit is Kelvin kilogram per mole. Or if we take this temperature in degree Celsius, the unit can be written as degree Celsius kilogram per mole. Now one more thing you see, delta Tf is equal to Kf into m, and we know m is the molarity, and molarity can be written mass of solute by molecular mass of solute into 1000 divided by mass of solvent. So we can use this formula also. Here delta Tf is again depression in freezing point of solution containing non-volatile solute. Kf is molar depression constant, or it is called cryoscopic constant, that depend upon the nature of solvent, and value of Kf is different for different solvent. And d is the mass of solute present in the solution. This capital MD is the molar mass of the solute dissolved in solution, and Ma is the mass of solvent in grams. And this colligative property can also be used, and this depression in freezing point is a colligative property, and this colligative property can also be used to determine the molecular mass of a non-volatile solute present in the solution. One more thing, how we can say delta Tf or depression in freezing point is a colligative property? So that already I told you, delta Tf is directly proportional to molarity of solution, and molarity depend upon number of mole of solute present per kilogram of solvent. So this property depend upon number of mole of solute particle present in solution, but does not depend upon nature of solute present in the solution. Now we can solve one to numerical problem based on this colligative property. You can write a statement: calculate freezing point of an aqueous solution containing 124 gram of ethylene glycol in 500 gram of water. Molar depression constant of water is 1.86 Kelvin kilogram per mole. This value is also given to you. Question is, calculate freezing point of an aqueous solution containing 124 gram of ethylene glycol in 500 gram of water. Means you have a solution, and this solution contains 124 gram of ethylene glycol. Ethylene glycol is CH2OH, CH2OH, and its molecular mass will be 24 plus 6 plus 32, means 62 gram per mole. Here there are 2 carbon atoms. The total mass will be 24. There are 6 hydrogen atoms and 2 oxygen atoms. So now we will apply the formula delta Tf equal to Kf into m, or we can write Kf into mass of solute by molecular mass of solute into 1000 divided by mass of solvent. So here delta Tf is equal to, we know the value of Kf is given 1.86, mass of solute 124 gram, molecular mass of solute is 62 into 1000 divided by mass of solvent is 500 gram. So if we solve it, delta Tf will be equal to 1.86 into 4, and it will be 6 for 24, 8 for 32, 34, and 4, yani 7.44 Kelvin. This is the depression freezing point of the solution. This is the depression in freezing point of the solution. Now we will calculate freezing point of the solution. So that will be TF naught minus TF. This is 7.44. Freezing point of pure water is 273 Kelvin, or you can take 0 degree Celsius. So TF will be, yani freezing point of the solution will be 273 minus 7.44. So it will be 265.56 Kelvin. Yani this aqueous solution, which contains 124 gram of ethylene glycol in 500 gram of water, will freeze at 265.56 Kelvin. So here we have calculated freezing point of the solution. One more numerical problem. You write freezing point of an aqueous solution containing 20 gram of a non-volatile solute in 200 gram of water is 270.5 Kelvin. Calculate molecular mass of solute present in solution. Here you see in statement what is given and what is asked. You are given with a solution containing 20 gram non-volatile solute, and solute is unknown, its molecular mass we have to find out, and 20 gram solute is dissolved in 200 gram of water, and freezing point of the solution is 270.5 Kelvin. Here Kf of water is also given to you, that is 1.86 Kelvin kilogram per mole. And we know the freezing point of pure water is 273 Kelvin. That already we know. That is 0 degree Celsius. So here delta TF will be equal to 273 minus 270.5. So it will be 2.5 Kelvin. Now we know delta TF is equal to Kf into mass of solute by molecular mass of solute into 1000 divided by mass of solvent. So delta TF is given 2.5, Kf is 1.86, mass of solute is 20 gram, molecular mass of solute we have to find out into 1000 divided by mass of solvent, that is water 200 gram. So here this you see molecular mass of solute will be 1.86 into 20 into 500 by 2.5. If we remove this decimal, 5, 5, 20, 5, 5 to 10, it will be 273 by 5, 372 by 5, so 7, 5, 35, 7, 4, 20, so it will be 74.4 gram per mole, unit of molecular mass. So molecular mass of this solute dissolved in the solution is 74.4 gram per mole. Okay, one more thing you see. Yesterday I told about Kb and today I told about Kf. Kb is called molar elevation constant and Kf is called molar depression constant. Kb is also known as ebullioscopic constant and Kf is also called cryoscopic constant. And value of Kb and Kf depend upon nature of solvent or nature of liquid, and their values will be different for different solvents or for different liquid. And value of Kb can be calculated from enthalpy of vaporization of liquid and its boiling point, normal boiling point. And you see Kb is given by this relation. You have to remember it. Kb is equal to RTB naught square by 1000 into LV. Here R we know that is universal gas constant, and value of R you have to take 8.314 joule per Kelvin per mole. Here this TB naught is the boiling point of liquid or liquid solvent, you can say. This is the boiling point of pure solvent, and here LV is latent heat of vaporization of liquid. And I think you know what the meaning of latent heat of vaporization. It is the amount of heat required to convert 1 gram of a liquid solvent, 1 gram of a liquid into its vapor state at its normal boiling point. Here you see latent heat of vaporization is per gram. This is the amount of heat required to convert 1 gram liquid into its vapor state at its boiling point. So for 1 gram of liquid, we need heat LV. So 1 mole of liquid will be equal to its molecular mass. Like if we take 1 mole of water, it will be 18 gram. If we take 1 mole of benzene, it will be 78 gram. Or if we take any 1 mole liquid, it will be equal to its molecular mass. So molecular mass of the liquid need heat LV into Ma. And this LV into Ma can be called enthalpy of vaporization of liquid. This is the amount of heat required to convert 1 mole of liquid into its vapor state. So I can write LV will be equal to enthalpy of vaporization divided by molecular mass of solvent. In this expression, so Kb will be equal to RTB naught square divided by 1000 into enthalpy of vaporization by molecular mass of solvent, and we can write Kb will be equal to RTB naught square divided by 1000 into enthalpy of vaporization, and this molecular mass of solvent we can write here. So Kb can be calculated from this expression or from this expression. If latent heat of vaporization of liquid is given, we will use formula Kb equal to R TB naught square by 1000 into LV. And if latent heat of vaporization की जगह enthalpy of vaporization is given, so we will write Kb equal to R TB naught square into Ma divided by 1000 into enthalpy of vaporization. In the same way, we can use formula for Kf, and Kf can be written as Kf will be equal to R Tf naught square divided by 1000 into Lf. Here R is again universal gas constant and Tf naught is a normal freezing point of pure solvent, and Lf is the latent heat of fusion. It is the amount of heat required to convert 1 gram of solid into liquid state at its normal melting point. And if we use enthalpy of fusion, So this formula becomes this one. Kf will be equal to R Tf naught square into Ma divided by 1000 into enthalpy of fusion. Or we know enthalpy of fusion is the amount of heat required to convert 1 mole of a solid into its liquid state at its melting point. So these two expressions for Kf also you have to remember. So calculation of Kb and Kf I have told you. Now one more thing about depression in freezing point. That you see, we know this correlative property, yani depression in freezing point can be used to determine molecular mass of a non-volatile solute present in the solution. And for that we have to measure depression in freezing point of that solution. And if we determine molecular mass of a solute present in a solution by measuring its depression in freezing point, it is called cryoscopic method. Yani cryoscopic method that is used for determining molecular mass of a non-volatile solute dissolved in a volatile solvent. When we measure the molecular mass of a solute by cryoscopic method, we generally use camphor as a solvent. Liquid camphor is used as a solvent for measuring the molecular mass of a non-volatile solute by cryoscopic method. And when we use camphor as a solvent for determining the molecular mass of a non-volatile solute, method is also called Rast method. In Rast method, we use camphor as a solvent, and camphor is preferred as a solvent because the molar depression constant of camphor is very high, and that is 39.7 Kelvin kilogram per mole. As the value of Kf for camphor is very high, so there will be more depression in freezing point of solution containing non-volatile solute, and that depression in freezing point, as it is high, can be determined, can be practically measured even using ordinary thermometer, normal thermometer. Here one question is generally asked, why camphor is preferred while measuring the molecular mass of a non-volatile solute by cryoscopic method or in Rast method? So camphor is preferred as a solvent because the molar depression constant or cryoscopic constant of camphor is very high, that is 39.7 Kelvin kilogram per mole, and due to higher value of Kf, there will be more depression in freezing point of solution, even small amount of solute is dissolved in camphor, and that high depression in freezing point of solution is easy to measure, and that's why we prefer camphor as a solvent while determining the molecular mass of a non-volatile solute by cryoscopic method. And using this Rast method, we generally determine the molecular mass of like naphthalene, anthracene, phenanthrene. These are highly soluble in liquid camphor. Now the applications or importance of depression in freezing point. First, in making of anti-freeze solution. of antifreeze solution. First you see what the meaning of antifreeze solution. We know in car radiators or in a radiator of vehicle, we use generally water as a coolant to keep the engine cool. But when car is used in sub-zero condition, mean where temperature is below 0 degrees Celsius, so water will freeze in the car radiator. And if you want to prevent freezing of water in car radiator, we have to add some suitable solute in water to make a solution. And we generally use ethylene glycol or glycerol in water to prevent freezing of solution in car radiator even in sub-zero condition. And in place of pure water, we should use aqueous solution of either ethylene glycol or glycerol in car radiator. Because this solution which contain ethylene glycol or glycerol in water has freezing point much lower than freezing point of pure water. And freezing point of this solution will depend upon the amount of ethylene glycol or glycerol added to water. So in severe cold condition or in sub-zero conditions, the freezing of solution can be prevented in car radiator by using aqueous solution of ethylene glycol or glycerol in car radiator which has freezing point below than 0 degrees Celsius. So such solution which we use in car radiator to prevent freezing even in sub-zero condition is called antifreeze solution. And for making antifreeze solution, we generally dissolve ethylene glycol or glycerol in water, and this solution will be used in a car radiator. Now second is use of de-icing agents. Use of de-icing agents. We know in European countries where there is a heavy snowfall, roads are blocked due to snow. And to make the road clear from snow, generally common salt sodium chloride or calcium chloride is sprayed over the snow. Because the mixture of sodium chloride and ice or calcium chloride and ice has much lower freezing point than that of pure ice or pure water. As NaCl ice mixer freezes at even -21 degrees Celsius, -21 degrees Celsius, and likewise calcium chloride and ice mixer freezes at even -55 degrees Celsius. So when sodium chloride or calcium chloride is sprayed over snow present over the road, ice will melt due to depression in freezing point. And these sodium chloride or calcium chloride which are used for melting of snow from the roads are called de-icing agents. And use of de-icing agent is also based on the phenomena that is depression in freezing point. So these are the two importances or application of depression in freezing point. One in making of antifreeze solution and second use of de-icing agents. Antifreeze solution are used in car radiator in sub-zero condition to prevent water in a car radiator. And de-icing agent are used for melting of ice from the roads or melting of snow from the roads. And both are based on concept of depression in freezing point. Here one interesting thing you see, we know a solution has lower freezing point than pure solvent and solution has higher boiling point than pure solvent. Like you see, suppose it is pure water. Water freezes at 0 degree Celsius and boils at 100 degree Celsius. So the range of temperature in which water remains in liquid state is 0 to 100 degree Celsius. But if we have some aqueous solution containing some non-volatile solute, that will be having freezing point lower than 0 degree Celsius and boiling point higher than 100 degree Celsius. यानी this aqueous solution which contain a non-volatile solute will freeze below 0 degree Celsius and boil above 100 degree Celsius. So we can say a solution containing non-volatile solute remain in liquid state in wider range of temperature. So the temperature range in which an aqueous solution containing a non-volatile solute will be more wider than the temperature range in which pure water remain in liquid state. Like pure water freezes at 0 degree Celsius, but this aqueous solution containing non-volatile solute will freeze below 0 degree Celsius. Water boil at 100 degree Celsius, but this aqueous solution containing non-volatile solute boils at temperature higher than 100 degree Celsius. So I can say a solution containing non-volatile solute remains in liquid state in wider range of temperature as compared to pure solvent. Today we have studied about third colligative property, and the property is depression in freezing point. You will make your own notes, try to understand this property, and if there is any query or doubt, you can respond in classroom.